Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking more about work in physics, and this time we're going to be talking about work kind of in the context of graphs in which I plot force versus distance and discuss how these graphs would relate to work. Tied to this is the idea of how do you figure out the amount of work done on an object if there is a not entirely constant force. Right, so we should begin the video by recalling that we've previously defined work as force dotted with displacement, or in other words that we might say work is F sub x times delta x. Now this is good as far as it goes. We maybe had some qualifications added to it that this could be the work done by a given force. It could also be the net amount of work if you take this force to be the net force. But the other major qualification to this is that this requires a constant amount of force. Or more appropriately, the force remains constant relative to the displacement. So you can have an object that is moving about some arc, and you're looking at friction. Friction kind of moves about the arc along with the object, and so we might say it has some constant value even though the direction of both displacement and force are changing. Relatively speaking, the two have a constant relationship. So this would work out for that, and the magnitude must be constant as well. But we also know that a lot of forces in nature aren't constant, and in fact when we push on something or pull on something, we can push or pull with a variable force. So simple examples of constant force. Constant force might include free fall acceleration near Earth. So free fall near Earth or near any other planetary surface. This one would give us a force of F equals mg. And so this is falling downward, the force is downward, the force has a more or less constant magnitude. Okay, but there's other types of force that are not so constant. For example, Hooke's law, so non-constant force, non-constant. We might have Hooke's law where the force is equal to k times x, or negative k times x. So it's in a constant direction relative to the displacement. It's always opposite the direction of the displacement, but the magnitude is varying. If I go farther away from the equilibrium, I have a larger magnitude of force. Okay, so this equation right here works out very nicely for the first case. It doesn't work out quite as easily for the second case. In fact, you might be told, okay, you have a spring and it's been displaced by a meter and it's applying a force of 100 newtons or something like that. So if you just said 100 newtons times 1 meter from when it starts to when it ends, you'd get 100 joules, but that's not the right amount of force. Even assuming an ideal Hooke's law spring, you'd actually only get 50 newtons worth of force out of that. So part of what we want to do today is consider how can we go about obtaining the work given a force that is not constant. And the answer is somewhat straightforward. Even in an algebra-based course, if you're in a calculus-based course, we would add something to what we're doing here. But in either kind of course, you could always look at the plot. And when you plot work versus when you plot force versus displacement, so you have force on one axis and you have displacement on the other axis, then whatever your graph is doing, as long as it's a function, if you want to get the work to move an object from point A, so let's call this one point A, to point B would be like maybe right here, then the area underneath this graph, bounded by the graph and the x-axis, is the work done. So area equals work done in basically moving from A to B. Okay, now if you're in a calculus-based course, or if you know some calculus, then you know that there is some way to get the work without referencing the graph, but by referencing the equation directly. Today, however, I'm focused more on if we have the graph and we know the numbers from the graph, can we find areas and therefore find works. An extension, by the way, to this is that if you want to find the potential energy for a system, you should figure out how much work did it take to get from 0 to whatever point your system is at. So that's kind of a little bit of an aside, but it goes with this statement. So let's say that you have a system in which you're at configuration C. So maybe you have like a rock that is at point C, which has some distance above the ground. Then the potential energy is the area under this same force versus displacement curve, but taken from wherever you've declared the ground to be, wherever you've declared potential energy equals 0 to be, over to point C. The caveat is that for most of these things we're doing here in Physics 1, it's like you have, let's say, like a rock on the ground and you lift it up, or you have a spring that you're moving from equilibrium. And so you usually end up taking 0 potential energy to be those positions. Those would be x equals 0. Sometimes it's actually advantageous to set 0 to be actually infinitely far away. We'll see cases like that when we discuss things like Newtonian law of universal gravitation or Coulomb's law in Physics 2. But that's a little bit of an aside. Let's come back to this idea. We're basically looking for the area under this curve. How do we get the area? Get the area one of two ways from a graph. And the two ways are kind of depends on how nice the graph is. Okay, one, for a nice graph, that is a graph that is linear or linear with cusps or horizontal lines and diagonal lines, something like that. You should break the graph into sections which are basically rectangles, and so the area of that area is base times height, and triangles, specifically right triangles, so that the area is 1/2 base times height. The other possibility, so this one right here would correspond to, for example, a graph like this. So here's your force, here's your delta x, and if you wanted to find your area to, let's say, this point right here and this point right here, then you can split it up into one triangle and one rectangle. On the other hand, a lot of forces do not give very nice graphs, so we'll call these curvy graphs. And if you have a curvy graph, then you're not really going to be able to split up very nicely into something like this. So maybe your graph is more like that. And for something like this, essentially all you can do is break up into the grid and count boxes. So for this type, count, you could call it count boxes or count squares in the graphing grid. So graph paper, for example. That's it. That's how you can go about trying to get these two area types. I have a quick example of a graph. So this one right here isn't meant to necessarily correspond to any particular physical thing, but let's say that you happen to have a system in which you can essentially get a force versus displacement graph that looks like this. So if we go ahead and put this in here, and maybe we want to find as our example the work done. So we might ask, how much work is being done to move this object from a starting location at 0 to an ending location of 10 meters. And to answer that, you basically want to find the area of under these curves. So this cusp point where it sort of breaks over is at roughly 5 meters. And you can break up this into basically 3 shapes. You have a rectangle here, a triangle here. So you could say area 1 is 1/2 of, and this is 10. If you look over here, this is 10 newtons, and then 5 meters. Then you have a rectangle here, which is, we could call this like area 2. Area 2 is 5 meters by 10 newtons. And then our third shape is this nice triangle here. We could call this area 3. And so this is 1/2 of, again, 5 meters for the base. And the height seems to be running from 10. This right here is 12. This right here is 14. This looks like about 12.5. So 12.5 minus 10 would give us 2.5. Okay, so if we solve for each of these, this first area, 1/2 times 10 times 5, is 25 joules. The second area is 50 joules. And the third area, 1/2 of 5 times 2.5, should be 6.25 joules. So our work done would be adding up all 3 of these areas, A1 plus A2 plus A3. So that should be 25 joules plus 50 joules plus 6.25 joules. And so our total work in this case is 81.25 joules. Now, if you're also keeping track of significant figures, you would maybe notice that there's no way that you have so many significant figures off of this graph. Probably you could get about 2. So we might call this about 81 joules worth of work. Okay, so that's all that I'm going to cover with this brief video. We have basically learned the general process for figuring out work done by a varying force under the conditions of having the graph of the force versus the displacement by finding the area underneath the curve. So hopefully you've learned something from this video, and thank you for watching.